Hello everyone. My name is Tony Valentine. I'm talking you to on behalf of Dedaub. We're a Web3 security company. We do auditing, we do security tooling, and kind of the topic of today's presentation is how to predict the impact of EVM upgrades. So today I'm going to be covering a couple of studies that my company did for the Ethereum Foundation last May related to 4 EIPs and the impact that they have on the EVM, both for past smart contracts and future smart contracts. So kind of an overview of what we'll cover in today's presentation. The first thing we'll cover is the self-destruct removal study. And so there's 2 EIPs for this. There's EIP 4758 and 6780, which have kind of different ramifications. I'll give you kind of a TLDR of self-destruct, the opcode. We'll kind of understand why it needed to go. Then we'll understand kind of how it was being used. And I'll give you the verdict of our study. The second thing I'll get into is the transaction and receipt route serialization changes. So that's EIP 6404 and 6466. We'll kind of understand what's changing and why it needs to change. Then we'll kind of figure out how to find contracts performing RLP decoding, since that's kind of one of the key things related to this EIP. We'll kind of find RLP blobs in call data, so we're trying to find transactions that are dealing with these RLP blobs. That's kind of related to the serialization. RLP is the serialization format used by ETH1. It's called a recursive length prefix. And then I'll give you the verdict of our second study. So yeah, as I mentioned, the first study is 4758 and 6780, and it's basically removing self-destruct from the EVM. So kind of a TLDR of self-destruct as an opcode. What self-destruct does, it clears your code, it clears your storage, and it resets your nonce to 0. It also lets you send all of the ETH in the address to a specified address of your choosing. There were also at one point gas refunds associated with this, and the whole point of adding this to the EVM was to promote state cleanup. So I don't know if any of you here run full nodes, maybe some of you run archive nodes, but the idea of promoting state cleanup for full nodes is to reduce the kind of footprint of running them. I think they're sitting at about 1 terabyte right now, which is kind of a bit heavy to run even on a modern laptop. So we saw kind of actually some abuses of this over the years. So a few years back there was gas token. I don't know if any of your developers, you might remember gas token. The whole idea of gas token is you could kind of spend gas when it was cheap and redeem it when it's high to offset future gas costs. And the way that this was done, it was by either creating a contract and then self-destructing it when gas was cheaper, or by writing to a storage slot and clearing that storage slot when gas was more expensive. And which one you chose depended on basically how much the gas price was going to increase. So if I believe anything under 3.5x, you would use the storage one, and anything over 3.5x, you would use the contract creation one. This abuse isn't actually the reason we wanted to remove self-destruct from the EVM, since it was mitigated with EIP 3529, which ended up slashing these refunds. Another kind of abuse we saw of self-destruct over the year was mutable code. So most people are under the impression that smart contracts are immutable. This didn't actually end up being the case after the introduction of Create 2, which I'll get into a little bit later. And it broke kind of the immutability guarantees that you had on chain. I'll give you the breakdown of the EIPs and then kind of explain why we ended up, why it needed to go. So EIP 4758 is what I can describe as deactivating self-destruct. So what we do is we rename the opcode inside the EVM. We rename it from self-destruct to send all. So it just sends all the ETH in your account. We don't touch the code, we don't touch the nonce, we don't touch the storage. And the whole idea here is to have reduced data transmission and state updates for light clients. So I don't know how familiar you are with the roadmap that Vitalik publishes. There's about 5 phases that were going on in parallel. One of them is known as the Verge. The Verge initially started off related to transitioning from Merkle trees to Verkle trees. But now it's become kind of a whole thing related to verification in general. The problem that self-destruct poses to Verkle trees, and the reason we want Verkle trees is for stateless light clients. And basically the whole idea there is that a client would only need to store the state root, and you would be able to send them all the data they needed to execute the state transition function and validate the new state root. The problem that self-destruct has is it has unbounded state updates. And what this means is for a given transaction, for a given block, you have a gas limit. That gas limit imposes a limit to how much you can actually do in a single block. So there are certain operations that cause state updates. Those would be creations. Those would be S stores. And if you take the amount of gas that they cost, you take the gas limit, you divide it out, you can figure out how much data you can actually needed to be sent in a single transaction. The problem self-destruct has is I can, over numerous transactions, numerous blocks, build up a lot of state variables. When I trigger the self-destruct, all of those state variables need to be reset to 0, and I would send a very, very large state update across the network. And the idea there is that it would interfere with consensus clients, especially these light clients. People on slower internet connections probably wouldn't be able to receive it in time. And if we move towards something like single slot finality, it could pose a real consensus issue. So that's kind of the whole idea behind it. EIP 6780, basically it's the same EIP as 4758. But what we do is we allow self-destruct if the contract is created inside the same transaction. The reason it's okay is because it's still bounded to the state update size of a single transaction. The reason that this was proposed is because it actually, has a reduced impact, and actually we saw this being used in practice in some protocols. So moving on to how we actually went about performing this study, we used Guest's or Aragon's tracing interface. And what this allows you to do is it allows you to replay historical data and actually hook into the EVM as it's executing. The things that we really care about for the sake of our study are capture start and capture end, as well as capture enter and capture exit. And these are used to model call frames inside of the EVM. There used to be a capture self-destruct, which I believe was an Aragon specific thing, but I'm not entirely sure. But nowadays, self-destruct events are actually modeled using capture enter and capture exit, which is actually quite interesting if you understand the inner workings of self-destruct, because self-destruct doesn't actually initiate a call frame when it transfers value. So essentially what you're getting is a pseudo call frame inside the tracing environment. And that's actually something we'll get into a little bit later. So we recorded all contract creations and self-destructs. We specifically, for the sake of our study, looked at the ranges from 50 million to 17.23 million. So those were the latest blocks at the time of our study. In that time, we saw about 9.5 million contract creations with 1 million creates, 8.5 million create twos, and then about 420,000 self-destructs. We ingested these into our database alongside all the other transaction data that we had, and we started running kind of analytical queries over this. And the first thing that we found was metamorphic smart contracts. So most people, when they want to have an upgradable smart contract, they use a proxy with delegate call. So delegate call EIP7 was actually introduced back in 2015 to enable people to have upgradable smart contracts, as delegate call allows you to basically keep the state in one contract, you forward the implementation logic to another contract, and it preserves the message sender and the message value, allowing you to basically upgrade your contract by pointing it to a new implementation contract. But by using create2 and self-destruct, we can actually upgrade our contracts in place. And the primary kind of users of this that we saw were MEV bots. So if you have an MEV bot, you've implemented a new strategy, you've added a new kind of like trading platform to it, you've optimized it, whatever. You have numerous, balances, allowances, maybe there's some soul-bound token associated with your MEV bot. If you want to upgrade it and transfer all that state over, some of it may not be transferable, it's a very expensive operation. So really you would want to, persist all of this state that you've built up associated with your account. And by upgrading it in place using these metamorphic patterns that I'll get into a bit later, you're able to be really efficient. We actually also saw this being used as kind of like a security, I don't know the best word to explain it, but we saw kind of hacks that were caused because of this. So we saw a Tornado Cash governance exploit. This happened after the OFAC thing, quite a bit after, where basically someone deployed a proposal. The proposal got accepted by the DAO. And then because they had deployed it using this metamorphic pattern, they were able to recreate the DAO proposal in place and execute malicious code against the DAO. We saw about 170,000 contract recreations. The top recreator had about 848 redeploys, and one MEV bot was deployed with 33 different bytecodes during its lifetime. So these are two patterns. There are a few others which enable you to do metamorphic contracts, or used to. And the top one is what we know as create 3. So basically you have your actor here, and what he does is he calls create 2 for a deployer contract. So this deployer contract is essentially acting like a proxy. It implements a function called deploy, and basically deploy is just a thin wrapper around create. And the reason that this is important is because the deployer has constant init code, and because it's using create, when it creates your contract, the address of this is determined by a hash of the address of the deployer and its nonce. And since we can reset the nonce of the deployer contract using self-destruct, and we can redeploy it in place using create2, we're able to recreate our metamorphic contract in place. The second pattern is quite a bit more complicated, as you can see. It's known as the metamorphic factory pattern. And so this has about 6 steps. So what you do is you have this factory contract on chain. You send it the code that you would like to deploy. It deploys it to some arbitrary address, doesn't really matter. It stores what the address of that contract is. It calls create2 with a constant init code to basically where your metamorphic contract will end up. And the init code of this contract does like 2 things. It queries the metamorphic factory for the address of this implementation. It does a code copy to copy all the code over, and then sets that as the return data. And by setting it as the return data, that's basically what the deployed contract will be. So because we're able to kind of do this loop, and this is created using create2, we can self-destruct it and redeploy it in place with absolutely no issues. The kind of the second thing that we saw is, basically self-destruct. It's a pseudo core frame. So generally, when you transfer value inside of the EVM, you have to actually send gas with it. Generally, if you do a solidity.transfer, you send about 2,300 gas. And this is basically enough gas to execute some small functionality inside the fallback function. The interesting thing about self-destruct is it doesn't actually do this. So when you execute a self-destruct, internally in the node, what it does is it looks up your balance, sets it to 0, and then increments the balance of whoever you set the address to. And the reason this is kind of interesting is because if we look at, for example, the WETH contract, the fallback function of the WETH contract calls deposit. And all deposit in WETH does is it increments your WETH balance and emits a deposit event. It doesn't actually do any accounting for how much WETH has been distributed. The way it actually calculates the total supply, it kind of does this optimization where it returns the ETH balance of the address. But by using self-destruct, what we're able to do is we're able to send ETH to the WETH contract without the WETH contract actually issuing any more WETH. And so what this means is that if we actually look at the total WETH allocations, and the way you look at the total WETH allocations is basically you track every single deposit event to find anybody who's ever had WETH. You look up their current balance using balance of. We have all of this data in a database. You sum that all up, and then you actually look at the ETH balance of WETH, and it's out by about 1,925 ETH. So the total supply is actually inflated. It doesn't pose any issues per se, since WETH is still fully liquid. You can always transfer one WETH into one ETH and one ETH into one WETH. But it's just an interesting accounting anomaly because of the fact that self-destruct doesn't actually hit fallback functions. And the reason that this is important is because we actually saw people using this to force send ETH. And what I mean by this is that if we have this nice transaction trace here from 3F neutral, and the line we care about is this. So we see that we've called create, we've set the value to 0.0125, and if I take the initialization code here and I run it through our decompiler, which essentially takes the bytecode and generates high-level code from it, it's one of the core technologies that we've developed at Dedaub. This is our initialization codes, and what you can see is basically we take the address at the end of the code and we call self-destruct on this address to send all the value to it. And that's actually what happens. We see the create, and then directly below it we see the self-destruct with the beneficiary, and we've copied the value. And we saw some protocols using this in practice. And kind of to give you the verdict of our study, we saw that there were about 10 protocols which we deemed affected by EIP 4758. And there were about 3 that we considered to be high impact. There were 0 protocols which we would deemed affected by EIP 6780. Both the proposals fixed this metamorphic contract issue that I mentioned to you. And as a result, the EIP was, 6780 was included in the Denkun hard fork, which happened about last month. Everything went smoothly, so we did a good job. Getting on to the second study, it's migrating root serialization from RLP to SSZ. And basically the whole thing here is related to ETH2. So I don't know if you're fully aware with ETH2 that happened after the merge, but essentially we have a separate execution layer and a separate consensus layer. The consensus layer uses this new serialization format known as SSZ, simple serialize. It has a few advantages over RLP. I've listed them over here, but the ones we care about specifically are that it is Merkle first and that it is indexable. And the reason why that kind of matters I'll get into later, but the Merkle first is very important, as I mentioned, for the Verge, for this thing of improving the verification powers of the network. So EIP 6404 wants to transition the transactions route from being a Merkle-Patricia tree, which is serialized using RLP, into a SSZ route, where basically the data is encoded using SSZ, and then we take the root of that data. And this change is basically being done to bring it in line with consensus. So when you get a consensus header, the transactions route is already SSZ, and when you get a transactions route on execution, it's RLP. So this change brings both of those in line. As for EIP 6466, the receipts route is an MPT on both consensus and execution, and this transitions it to being SSZ for both of them. So kind of the important thing that we need to understand for this is that currently contracts are dealing with Merkle-Patricia tree routes which are serialized with RLP data. So we really want to look for contracts who are using this data, and to use the data they have to be dealing with decoding, manipulating somehow RLP data. So in order to do that we need to kind of first understand what RLP data looks like. So this is the schema for RLP encoding and decoding. There's like 5 cases. You have a single byte, a string of bytes, a long string, a list of items, or a long list of items, and each one has kind of like a prefix code associated with it. I can kind of present this more clearly by showing you some pseudocode, and we can see we have a nice if-else chain where each one is bounded by one of these RLP constants. And so this kind of function is what we want to look for on-chain. We want to find contracts that have this pattern in their code. And how do we go about doing that? It's kind of a hard problem. The key insight that we kind of had at the time was that because RLP data is dynamic, because it is non-indexable, as I mentioned, indexability is one of the advantages of SSZ data, is that because it's dynamic, it's non-indexable, you have to have these constants. If you do not have these constants, then you cannot possibly be dealing with RLP data since you can't decode it correctly. So what you can do is you can take a look at the bytecode, and this is a disassembled view of the bytecode. you can look for push operations which have these RLP constants. So if they don't have the constants, can't be doing RLP decoding. So if you just naively search for contracts that have the requisite constants, you get a result set of about 26.6 thousand results, which for a 2-week study is unmanageable. So we needed to be a bit more clever about how we went about filtering this set down. And so really, when we think about it, we don't care that the contracts have RLP constants. We care that these constants are being used in comparison operations. And so, as we can see, we push this data, and then we have a comparison operation. But we have this dupe 3 in the middle. And we can actually have numerous stack operations between our data being pushed and between our comparison operation. And we really want to kind of abstract all of this away. And as I mentioned, one of the technologies that we have at Dedaub, which is also available publicly on GitHub, it's GigaHorse, it's our decompiler. And that's actually what we have here. We have a 3-address code representation of the same bytecode. And what we can see is that we actually have this RLP constant, the 0xC0, being used in a comparison operation. We have less than variable RLP constant. And because we index the entire blockchain, we've decompiled everything on chain, we're able to run this nice SQL query down here against the 3-address code. And we're able to filter out all the contracts that have them using comparison operations. The actual query we ran is nowhere near this neat. It's like a horrible regex monstrosity because you need to account for like plus and minus 1. You need to account for like greater than or equal to. You need to account for it being on like the right-hand side or the left-hand side. It's a mess. I've linked it at the end if you care, but it's a mess, trust me. So if we just look for comparison operations in the attack, we get about 556 results. That's like an order of magnitude better. It's actually manageable in a 2-week study. But we're engineers. We think we're clever. We think we could do better. So we went about doing what we call a data flow analysis. So I'll move a little bit over here so you can see. And so what we have here is we have a data flow analysis. And basically what we want to do is we want to make sure that the result of this comparison operation actually dictates the control flow. So we have the red variable here is used in the comparison operation. It flows into the green variable. The green variable flows through an is0 operation into the purple variable. And then the purple variable is used as the conditional of a jump I. So what that means basically is the purple variable dictates whether we jump a block or whether we fall through to the next block. So it is dictating the control flow. And that's what an if statement is. An if statement, you have a Boolean expression that dictates the control flow. Either you enter the if statement or you enter the else statement. And so running the data flow analysis and combining with transaction data, we get about under 100 results, which is incredibly manageable in a 2-week kind of slot. So we went about doing this. Some of our team went about kind of investigating these results. But the rest of our team, we kind of wanted to find another way to find RLP contracts. And we wanted to do this by looking at call data. So if we're going to look at call data, we need to understand how call data is encoded. So this is the Solidity ABI specification. There's also 5 cases. That lines up nicely. And the one we really care about is dynamic size types, because the RLP data will be passed as a bytes object to a contract. So if we look at how a bytes object will be encoded, this is kind of the way it works. So if we encode 0xABCDEF as bytes, the first thing we do, we take the length. So 6 hex characters is 3 bytes. And so we take 3, we make it 32 bytes, so we pad it, and we prepend it to our data, ABCDEF, padded to 32 bytes. And as you can see, we have a very efficient encoding scheme. So the key insight that we had here related to how call data is encoded is that we have a length field, and RLP data, recursive length prefix data, also has a length field. So could we possibly use the synchronicity of these 2 length fields to find RLP data inside of transactions? And the answer is yes. So if we look at the word X here, we have 217. And if we look at the word Y here, we have the beginning of an RLP blob. And so this data starts with F9. That's a long list. The way you decode a long list is you subtract F7 from it, and you get 2. And what that 2 means is 2 is the size of the length field. So the next 2 bytes, 1, 2, encode the length of the rest of the data. So the rest of the data from this point A onwards is 214 bytes long. And so what we can do is we can add 214 to the length of this, which is 2 bytes, and the length of the prefix, which is 1 byte. 217 plus 2 plus 1, quick maths, they both equal 217. And so we can say with some certainty that this is actual RLP data, because the chance of this happening with any 2 words inside of call data at random is astronomically low. So we gathered a data set of transactions that contained RLP data. We got the contracts that were involved in that. We got the contracts that we got using our other method. And we started going around kind of manual investigations. And the result of our manual investigations was kind of as follows. So most of the bridge applications on Ethereum were unaffected because most people are bridging from either L1 to L2 or L2 to L1, and L2 wasn't changing. So the only bridge applications that were actually doing L1 to L1 proofs were Layer 0, ZK Bridge, which I believe builds on Layer 0, I can't remember correctly, and telepathy. And kind of another important thing that we noticed is EIP 6466, which is the receipts route change, actually was the only change that had an impact. The transactions route change 6404 didn't really see use for doing L1 to L1 proofs. So we didn't see people doing transaction inclusion proofs from L1 to L1, but we did see people doing log inclusion proofs from L1 to L1. So that's kind of all I have time for today's presentation. You can scan this QR code if you want a link to some resources related to, for example, The Verge. There's also my slides. There's also some of the queries we ran along with that horrible regex that I added. I wrote it. You're going to have to read it. And yeah, that's about all I have for you today. If you have any questions, I'm more than happy to take any. I don't know how much time I have.
We have another 5 minutes, so.
Okay, so any questions?
Going once, going twice. Are we all going to have beer?
I'm good for that.
Okay.
All right, let's go party.